So now we're taking a look at the area of the sector. So theta is in principle the same, and r is in principle the same, and so we're just going to find the area of this sector now. Well, you have to think back, what's the area of a circle? Well, the area of a circle is also in terms of the radius, but it's the radius squared, because we're talking about a surface as opposed to just a linear amount. And it turns out to be pi times r squared. This is the same pi as before, it's about 3.14. A little bit less than 22 over 7. The fraction of the full angle that we've swept out is still the same, right? It's theta divided by 2 pi. And as it turns out, I don't think it's too hard to convince yourself, that this arc length is the same fraction of the circumference that the area of this sector is to the full circle, right? This area divided by the full circle's area is going to be the same fraction as this arc length divided by the full circle's arc length. And so to find the area of the sector, we simply multiply the area of the full circle by the fraction that we've swept out, which is again theta over 2 pi. Now we get a cancellation. It's not quite as nice. Just the pi's cancel, and we're left with this factor of 1/2, and we get that the area of the sector given theta and the radius is exactly equal to theta times r squared over 2. And this is in radians, by the way. Again, if we were to convert to degrees, we'd have to replace theta by 180 over pi times theta, and that gives us this horrendous thing. 180 divided by 2 would simplify, and we would get 90 r squared over pi. And apparently that's the area, right? Because theta would have to be multiplied by 180 over pi, and then 180 over 2 is 90, and so then you get this as your area. This is the units with this terrible conversion factor of 90 over pi as your units for this. Whereas if you just use radians, even though the units for a full circle turn out to be irrational, they give much, much nicer formulas. So we're going to stick with radians from now on, and that's going to really, really help our trigonometry, because the bedrock of trigonometric units is essentially radians. Degrees would make the graphs much, much longer than they need to be. No more difficult or anything, it's just, it's much, much easier to use numbers that are smaller, right? 360 being one circle is much more cumbersome than just 2 pi. 2 pi, may be irrational, but it's only 6.28-ish, so it's considerably less than 360, which means all of our inputs are going to be drastically smaller, easier to work with, and we have this nice symbol for exact amounts of pi and full circles, so it's not like it's that big of a deal, right? We just write this symbol and we mean more or less some nice fraction of the circle. So even though the units are irrational, formulas are better, and trigonometry will be much, much easier to deal with than having to do a lot of degrees. So we're going to stick with radians from now on. One last thing I wanted to point out before the end of the video is how to convert some of our special angles that we investigated in special right triangles. How do we convert them from degrees to radians, right? So we just got to use that same conversion factor that we learned before. So I'm going to show you the 5 main angles that you're going to want to remember that get converted from degrees to radians quite often, and that we're going to need to know when we investigate the special values of trigonometric functions. So here we go. So the 5 you're going to want to know are 0 degrees, 30 degrees, 45 degrees, 60 degrees, 90 degrees. When we get to the unit circle, you will see that all of these angles correspond to parts of the circle that are in the first quadrant of the xy plane. You're going to be able to just sort of translate these values to other parts of the graph, and then you don't have to remember as much. So for now, we're just focusing on these amounts. Well, remember, so this is degrees, and this is radians. And remember, what's the conversion factor for radians? It's pi divided by 180 times the amount in degrees. So 0 degrees times pi over 180, well, we can write it out, pi divided by 180 times 0. Well, what's anything times 0? This is going to be equal to 0 radians. That's not too difficult to believe, right? So 0 degrees is 0 radians. 30 degrees times pi over 180. Well, 30 divided by 180 is going to be the same thing as 3 divided by 18, right? Because they both share a factor of 10. And 3 goes into 18 6 times. So 30 divided by 180 is going to be the same thing as 1 divided by 6. So this, the factor of pi, comes along for the ride, and we're left with pi divided by 6 radians, right? Not too difficult. 45 degrees, same idea, right? Pi over 180 times 45. Now, 90 degrees is half of 180. since 45 is then half of 90, that must make 45 1/4 of 180. So this will simplify to 1 over 4. Pi comes along for the ride, and we're left with pi over 4 radians. 60 degrees, pi divided by 180 times 60. Well, 30 divided by 180 was pi over 6. 60 is 2 times more than that, right? So 60 divided by 280 is not going to be 1/6, but what's 2 times 1/6? That's going to be 2/6 or 1/3, right? So this is 60 over 180 is going to be 1 divided by 3. Again, pi comes along, and we get pi divided by 3 radians. And 90 degrees is probably the easiest, other than 0 degrees. All we have to do is multiply 90 by pi divided by 180, and since 90 is half of 180, that must make 90 divided by 180 the same as 1 divided by 2, times pi gives us pi over 2 radians. Now let's confirm. Two angles that add up to 90 degrees, what we call complementary, right? 0 plus 90 is 90, 60 plus 30 is 90, 45 plus 45 equals 90. Now, this one is pretty easy to confirm, right? 90 divided by 180 is 1 over 2, times pi gives us pi over 2. So similarly to how two angles adding up to 90 degrees makes them complementary, two angles that add up to pi over 2 radians are also complementary because these things are equal, right? 90 degrees is pi over 2 radians, just like 1 meter is pretty much exactly 3.3 feet. So if two angles add up to pi over 2 radians, that must mean that they're complementary. Well, 0 plus pi over 2 is pi over 2, so they're complementary. Pi over 6 plus pi over 3. Well, pi over 3 is the same as 2 pi over 6. 2 pi over 6 plus 1 pi over 6 equals 3 pi over 6. 3 pi over 6 is the same as 1 pi over 2, and so these two angles are still complementary. Pi over 4 plus pi over 4 is the same as 2 pi over 4, which simplifies to pi over 2 as well, which means that this plus itself, which is 45 degrees plus 45 degrees, is still pi over 2 radians, or 90 degrees. So that was just to confirm that we did our math right, and that pairs of complementary angles do in fact add up to the thing that I said was equal to 90 degrees. So these are the numbers we're going to be using quite a lot. And you may recall that we did in fact derive the sine of these three numbers. If you remember, the sine of 30 degrees is 1/2, which means that the sine of pi over 6 radians is also 1/2. Now that, keep in mind, that does not mean that the sine of pi over 6 degrees is 1/2. Pi over 6 degrees is actually a really tiny amount, right? Because degrees in and of themselves are really small. Pi is about 3. Dividing that by 6 means that you get about a half of a degree. So the sine of that is going to be rather tiny, you'll find, when we actually see what the functions represent with regards to circles. But the point is that the sine of 30 degrees is 1/2, so the sine of pi over 6 radians is 1/2. The sine of 45 degrees is root 2 over 2, so the sine of pi over 4 radians is root 2 over 2. And the sine of 60 degrees is root 3 over 2, which means the sine of pi over 3 radians is also root 3 over 2. We will derive the sine values for 0 and 90 degrees when we get to unit circles in the next video. I know I said that I was going to do that this time, but I figured it was good to cover these basics. So now that we've done all that and discussed radians and what they mean for area and lengths in circles, I think it's time to finally move on to the unit circle. Thanks for watching.